Hello and welcome. In this lecture, we are going to learn uniform circular motion. Now, what is a uniform circular motion? An object is said to be in a uniform circular motion if it travels around a circle or a circular arc. So, if this is an object moving in a circular arc like this object is moving in a circular path, we say that it is in uniform circular motion. At every instant of time in a uniform circular motion, the velocity is tangential to the circular path. So at this point, velocity is directed in this direction. At this point, velocity is directed in this direction. At this point, it is directed in this direction. And at this point, it is directed in this direction. Since velocity is changing directions, we say that it is accelerating. We say that the object is accelerating, although the velocity magnitude is constant. This acceleration is directed towards the center of the circular path, like this. This acceleration is directed towards the center of the circular path. This acceleration is called centripetal acceleration. Now we will derive the relation for centripetal acceleration. Suppose this object is moving in the circular path. The velocity of the object is v. The center of the circular path is located at origin. The radius of the circular path is r. And let the object is currently located at point P with coordinates xp and yp with coordinates xp and yp, and let the line OP make an angle theta with the horizontal direction. We can write velocity vector as Vxi plus Vyj. Velocity vector is Vxi plus Vyj. Now we would like to write Vx and Vy in terms of angle theta. We would like to write Vx and Vy in terms of angle theta. So we can see that in this triangle OAP, let this point be A. Therefore, this triangle OAP is a right angle triangle and this angle is 90 degrees. Therefore, this angle will be 90 minus theta. This angle will be 90 minus theta. This angle will be 90 minus theta. And since the velocity vector is tangential to the circular path, this angle will be 90 degrees. Therefore, this angle will be theta. This angle will be theta. Now we can resolve this velocity vectors in terms of component, and we can see that x component is directed in this direction and y component is directed in this direction. Since this angle theta is adjacent to the y component, therefore y component of the velocity is v cos theta, and since the x component of the velocity is directed in the negative x direction, x component of velocity is minus v sine theta. X component of velocity is minus v sine theta and y component of velocity is v cos theta. Therefore, velocity vector can be written as minus v sine theta I plus v cos theta j. Now we can see that sine theta is yp by r, sine theta is yp by r, sine theta is yp by r, and cos theta is xp by r. Therefore, we can write velocity vector as minus vyp by ri plus vxp by rj. Now to determine acceleration, we take the derivative of velocity with respect to time. Therefore, acceleration is a equal to dv by dt. For taking the derivative, we realize that v and r are constant. They don't change with time. Only xp and yp change with time. Therefore, while taking the derivative, v and r will act as a constant. Therefore, acceleration vector will be minus v by r dyp by dt I plus v by r dxp by dt j. Now, dyp by dt is equal to vy, this is equal to v cos theta, dyp by dt is vy equal to v cos theta, and dxp by dt is equal to vx equal to minus v sin theta. Dyp by dt is y component of velocity, which is equal to v cos theta, and dxp by dt is equal to x component of velocity, which is equal to minus v sin theta. Therefore, acceleration vector is minus v square by r cos theta I plus minus v square by r sin theta j. The acceleration vector is minus v square by r cos theta I plus minus v square by r sin theta j. Okay, so now we have obtained the acceleration vector as a is equal to minus v square by r cos theta I plus minus v square by r sin theta j. This is the x component of acceleration and this is the y component of acceleration. The negative sign indicates that both are directed radially, both are directed inwards. Both x and y components of acceleration are directed inwards. So if this is the object moving the circular path, this is the object moving the circular path, the x component of acceleration is directed like this, and y component of acceleration is directed like this, and this is the direction of the resultant vector A. We can find the magnitude of A by summing the squares of components and taking the square root. Therefore, magnitude of A is equal to square root of ax square plus ay square. We can see that in both the components v square by r is common. In both the components v square by r is common. So we can take this out of the square and ultimately out of the square root to obtain a equal to v square by r square root of cos square theta plus sin square theta. Now we know that cos square theta plus sin square theta is 1. Therefore, magnitude of centripetal acceleration A is equal to v square by r. Magnitude of centripetal acceleration A is equal to v square by r. Now we will show that this acceleration is directed radially inwards. Suppose that the acceleration vector A is making an angle phi. Acceleration vector A is making an angle phi with the horizontal direction. Then tan phi will be ay by ax. Putting the value of ay by ax, we find that tan phi is equal to minus v square by r sin theta divided by minus v square by r cos theta. Minus v square by r cancels out. Sin theta by cos theta is tan theta. Therefore, tan of phi is equal to tan of tan theta. This means that phi is equal to theta. Recall that theta is the angle made by the line joining the center to the position of the object with the horizontal direction. This means that phi is theta. Phi equal to theta means that acceleration vector is directed radially inwards. This means that acceleration vector is directed radially in. Now, another question we will like to address is the time taken by the object to complete one revolution. This time is called period of revolution. So we will now obtain the period of revolution. In one revolution, the object covers a distance equal to the circumference of the circle. So the distance covered is circumference, and the speed by at which the distance is covered is the magnitude of velocity. Therefore, time period of revolution is equal to circumference divided by velocity magnitude. Circumference is 2 pi r, velocity magnitude is v. Therefore, period of revolution is given by equation t is equal to 2 pi r. For a better understanding, we will take an example. It is given that an Earth satellite moves in a circular orbit 640 kilometers above the Earth's surface with a period of 98 minutes. We are required to find the speed and magnitude of centripetal acceleration. We are required to find the speed of the satellite and magnitude of the centripetal acceleration of the satellite. So if this is the Earth, the satellite is moving around the Earth in a circular orbit. The distance of the satellite from the Earth's surface is d. We can assume that this distance is d. Now we are given that the time period of the rotation of the satellite is 98 minutes. Therefore, period of revolution of the satellite is t equal to 98 minutes. This is equal to 98 into 60 seconds. We are also given that d is equal to 640 kilometers. To find the radius of the circular path, we need to know the radius of the Earth, and we have to add to the radius of the Earth the distance of the satellite from the Earth's surface. Therefore, r, which is the radius of the circular path, will be equal to d plus r, where r is the radius of the Earth. Now, radius of the Earth is approximately equal to 6360 kilometers. It is approximately equal to 6360 kilometers. Therefore, radius of the circular path will be equal to 640 plus 6360 kilometers. This will be equal to 7000 kilometers. Therefore, the radius of the circular orbit will be 7000 kilometers. This means that in meters, r is equal to 7000 into 1000 meters, and this is equal to 7 into 10 to the power 6 meters. Now we are given that time period of revolution is 98 minutes, and which is equal to 2 pi r by v. From this we can obtain velocity magnitude as v equal to 2 pi r by t. Putting the values of r and t, we can obtain v as 2 pi into 7 into 10 to the power 6 divided by 98 into 60. And if we calculate it, we will find that v is equal to 7476.2 meters per second. Therefore, the speed of the satellite is equal to 7476.2 meters per second. Now we will obtain the magnitude of centripetal acceleration. We know that it is given by centripetal acceleration is given by A is equal to V square by R. Putting values of V and R, we find that A is equal to 7476.2 square divided by 7 into 10 to the power 6. And if you calculate it, we'll find that magnitude of centripetal acceleration is equal to 7.98 meters per second square. This is the magnitude of centripetal acceleration. So we have obtained the speed of the satellite, and we have obtained the magnitude of centripetal acceleration. That's all for today. In the next video, we will learn about relative motion in 2 dimensions.